Welcome back. In the previous lecture, we had discussed oxidant utilization in the fuel cell. In this lecture, we will look at fuel utilization. So the most common fuel in a fuel cell is hydrogen. When in a proton exchange membrane fuel cell, uh, hydrogen forms proton inside the electrolyte. So the utilization of the fuel can be defined in the following manner. Rate of hydrogen consumption is given by current density times the active area available in the fuel cell divided by NF, where N is given by 2 based on this reaction. The rate of hydrogen being supplied is given by the mass flow rate of the fuel divided by the molecular weight of the fuel would give you the molar flow rate of the fuel times the mole fraction of hydrogen in the fuel stream. So it might not be 100% hydrogen. So there is a certain mole fraction. This quantity gives the rate of hydrogen being supplied. So this way we define the utilization of the fuel, in this case, hydrogen. In contrast to the oxidant, in the case of an oxidant stream, the unused oxidant can be let out in the ambient air, but this is less desirable in the case of a fuel stream. And in addition, hydrogen is expensive. You would want to utilize it more. So what is done typically is some part of the stream that comes out of the fuel cell stack is recycled back. So this is the molar flow rate of the recycled stream, molar flow rate of the new fuel stream. These two are mixed and sent into the fuel cell stack. So there are different ways in which you can define utilization of the fuel. Nothing conceptual, just the different ways of defining utilization of the fuel. So here is the current from each cell. There's the number of cells. This gives you the rate of hydrogen consumed in the stack divided by the hydrogen supplied to the system. That is sum of these two. Another way of defining is utilization based on this stream, that is in the denominator. Only this times the mole fraction goes. Okay, these are nothing very conceptual. There's a matter of definition. So, and the recycle ratio is defined as this divided by this. But this is more conceptual. Let's pause a little bit here. Most of the fuel cell, or in fact, almost all of the fuel cell, have a fuel processing step. The fuel processing step might involve, let's say, removal of certain impurities, or in some cases, it might be more complicated, wherein some catalytic reaction via a heterogeneous catalyst occurs in this fuel processor. Sometimes it might be a reforming reaction that occurs at a particular temperature. And depending upon the temperature of the fuel cell stack, that reforming reaction may continue to occur in the fuel cell stack also. In some case, the exhaust of the fuel cell stack is recycled back into the fuel processor. So the composition of the fuel processor can be quite complex, and the reformate stream that gets into the fuel cell stack might have many components. It may have hydrogen and carbon monoxide. Both can be oxidized. Therefore, both can act as a fuel. It may have H2O. It may also have some nitrogen that is recycled back in some cases. So one way of defining utilization of the fuel is rate of equivalence consumed in the stack divided by the rate of equivalence supplied to the stack. Let's understand what we mean by equivalence. The best way to think about it is in terms of electrons. For example, if you have hydrogen as a fuel, for 1 mole of hydrogen, 2 moles of electrons are generated. So for 1 mole, there are 2 equivalent moles of electrons. In a previous lecture, we had used a generic fuel with this chemical formula. Based on stoichiometry, this much amount of oxygen is being utilized. And as mentioned earlier, for 1 mole of O2, 4 moles of electrons are utilized for reducing O2. Therefore, this times 4 is the amount of equivalent electrons that is being consumed for 1 mole of the fuel. So the rate of equivalence has to be thought through in terms of stoichiometry, the amount of electrons that are equivalent to the fuel. In this case, it's 2. In this case, it is this much. That goes into the rate of equivalence, and that is consumed in the stack divided by the rate of equivalence that is supplied to the stack. So you can have another efficiency, that is the rate of equivalence of oxidizable fuel supplied to the stack, that is this stream, divided by the rate of fuel supplied to the fuel stream, that is that corresponds to equivalence present here. There is a reforming reaction that occurs here, so it may become fuel rich, as in this stream might be more rich in fuel compared to this stream. And this stream might also have components coming from this stream. So these two, when multiplied, gives you this overall formula, which is the eta, the efficiency of a fuel cell, of the fuel. Okay, so that when this is multiplied, the rate of equivalence consumed in a stack divided by the rate of equivalence of the fuel supplied to the fuel processor. Okay, so this in terms of the denominator is in terms of equivalence present in the fuel. In a way, when we multiply these two quantities, what we are doing is we are indicating one aspect, this aspect corresponding to this subcomponent. This component, this particular factor corresponds to this subcomponent. So another way of defining eta fuel processing, instead of using rate of equivalence, we can also talk in terms of heating value of the fuel supplied to the stack. We have already elaborated in a previous lecture what we mean by heating value. And in the denominator, we denote the heating value of the fuel supplied to the fuel processor. So the fuel, if it gets enriched in the fuel processor, so this quantity will be more than this quantity. Many factors in a fuel cell are coupled. For example, water removal involves a particular trade-off. In a proton exchange membrane fuel cell, water, H2O, that is the product of the reaction, is formed in the liquid state. If lot of water accumulates in the fuel cell, that may impose additional mass transfer limitation, preventing O2 from reaching the electrode. That is not desirable. So you want to remove some amount of water. But if you remove a lot of water, as you know, it is in a PEMFC, the electrolyte contains water. The conductivity of the electrolyte is crucially depends on the amount of water present. If the membrane gets dried out, it significantly decreases the conductivity of proton. So that is not also desirable. Too less removal of water or too much removal of water, both these extremes are not desirable. So there should be an optimal trade-off in the removal of water to maintain a balance in terms of proton conductivity and in terms of mass transfer resistance for oxygen to reach the electrode. So a lot of engineering goes into all these things. For example, in SOFC, the air serves multiple purposes. Air is obviously the oxidant. Oxygen is part of air. So air serves as an oxidant in solid oxide fuel cell, but it also plays an important role. SOFC operates at a very high temperature. So heat removal is very critical in SOFC, because if you have a lot of heat that is being generated, which is not removed, it leads to material degradation and fuel cell degradation. So one of the role of air in an SOFC is to act as an agent for removing heat. So if you supply too much of air, you may cool down the SOFC. If you do not supply enough air, you may not have enough air to remove heat from an SOFC. Again, all these things involve a lot of engineering. In a way, operating a fuel cell system is like operating a process intensified chemical plant, right? There's a reformer, there is a stack which does different things, and there are pumps, power conditioning units, and so on. So it's like a mini chemical plant. So a lot of chemical engineering goes into designing the fuel cell system per se. In the next lecture, we will look at aspects of flow design in a fuel cell system. Thank you.